Alright, today we start our camper build, so let me show you what I have going on this truck. This is my 2005 Toyota Tundra. It's a two-wheel drive version that I'm slowly converting into my overlanding rig. I just bought this ARE high topper. It's a used topper, but fairly decent condition. Let me show you what the inside looks like. The nice thing about this topper is that it has a fold-down window in the front, so I can easily clean the cab, the window of my cab. Sliding windows on both sides. And I do like the high topper because it gives me that extra headroom, since I'm a fairly tall guy. Because this is a used topper, it does have some issues with it. It's got a delamination issue here going on, so I need to glue that together. It's missing this metal bracket that interfaces with the latching mechanism for the hatch. So this side has it, this metal bracket here, and it has this little opening that the latch interfaces with. So this side is missing that, so I need to remake this metal bracket. But it interfaces with this portion here, the latching mechanism. So right now, the driver's side of the hatch doesn't lock. I'm ready to start the camper build portion for this truck, and so I'm going to have a bed platform back here. It's not going to be anything fancy, but just something comfortable. My only requirements is that I want to be able to sit up straight in here without my knees in my chest or my head bonking the top of the shell. These Tundras have fairly low bed rail heights. This is 18 inches from the top of the rail to the bottom of the bed. So my bed is going to be at least as high, if not higher, because again, I don't want my knees in my chest when I'm sitting on this bed. So when it's that high, my head is already brushing up against this topper. And so my solution is to build a topper lift. So at each of the four corners of the topper will be a mechanism that raises the shell 18 inches. And that will give me the extra headroom that I'm looking for, while still giving me that nice seating position that I'm looking for. So let me show you what my mechanism to raise the topper is going to look like. So this is my mechanism that I'm using to raise and lower my shell of the truck. I modeled the truck bed in SolidWorks. This light blue part is the bottom of the topper itself. The mechanism to raise the topper is a linear actuator. This is the part in magenta. The linear actuator is attached to this green square rectangular tubing, and it's telescoping into this yellow portion. This yellow portion is bolted to the truck with one screw here, and there'll be two screws that go into the side of the bed here. The telescoping green rod or square tube is bolted to this brown upright. So the brown upright looks like this. This brown upright is bolted to the top itself, the topper itself, the bottom of the topper. So if this is what you see of the topper, the bottom of the topper on the inside of the cab, I'll probably have a 1/8 inch or maybe a 0.94 thick aluminum plate underneath, sandwiching the topper to this brown upright, give it support. Now the reason I'm going with the telescoping mechanism instead of just this linear actuator is because I don't know a whole lot about this linear actuator. I don't know what kind of lateral loads it can take. I don't know its durability or its how well built they are. I just don't know anything about them. So for maximum safety's sake, I went with this telescoping rod design. And so when the linear actuator is all the way in the up position, and by the way, I got linear actuators that turn off once they're fully extended, and they turn off automatically once they're fully collapsed. So I don't have to do any fancy wiring with these. It's all self-contained in the linear actuator itself. But once the linear actuator is in the fully up position, there's going to be a shear pin that goes through these two telescoping parts. So there'll be a hole in the shell part and a corresponding hole in the screen part, and then I'll put a pin in once it's fully extended. And so that shear pin will handle all the loads of the top pushing down. The telescoping rods will handle all lateral loads. So top is up and it's really windy. This will handle all the lateral loads, so the linear actuator doesn't have to handle any of that. The telescoping rod will handle all that, the lateral loads. The shear pin will handle most of the loads coming down. So again, if you have 5 feet of snow on your topper, the shear pin will handle that entire load. That way the linear actuator doesn't have to handle that. But you do have two factors of safety now. You have this linear actuator holding the top up, and you have the shear pin holding the top up. So I'll go through some of the calculations on, the stress calculations, the shear calculations of how strong the shear pin is going to be and all that. I'll show you how I do that after this segment of the video. But once the top goes down, I have this tongue and groove piece here. So there's a groove piece on the brown upright, and then there's a tang on this lower part. These two interact to prevent fore and aft and lateral movement of the top. So I was going to use the stake bed pockets, but there are other things that cause issues that would have made it more difficult for me to incorporate these stake beds. So I just went with this tongue and groove type situation here. And again, I'll go through the calculations to show you that, yes, this is going to be strong enough to handle the loads, that the dynamic loads this top is going to see when you're driving. Now, when the top is closed, that same pin that was holding the top up is going to be holding it down also. So there will be a corresponding hole in both of these parts when the top is fully in the down position. In addition, there's going to be a hold down clamp here, and this hold down clamp looks like this. So it's a pull down clamp. So this part is what I just showed you on the SolidWorks drawing, and then this part here will get mounted to the upright itself. So these 4 holes on the uprights will handle the body of the clamp. So as the top comes down, the clamp pulls everything really tightly together to the bed. You insert the shear pin, acts as an additional lock, and of course the linear actuator acts as an additional lock. So now you have 3 factors of safety. You have the linear actuator, you have the shear pin, and you have this clamp holding the truck bed, holding the topper to the truck bed. And then again, all the fore and aft lateral movements are handled by this tongue and groove situation here. So I'll have 4 of these at the corners of the truck bed to support the weight of the topper. Before I can build out the camper portion, the putting out the bed and all that stuff, I need to get these done because these do take up a bit of real estate in the bed, and I want to be able to make everything around these uprights. So I need to get these done before I can get the sleeping area done in this truck. So in the next section, I'll show you how I go through some of my calculations. I'll show you how I figure out some of the loads that I think this top is going to see when you're driving and when it's in the up position. So whenever I design a widget that's going to be doing something, I always want to look at the loads that it's going to be experiencing. So if I'm designing a lift mechanism that's going to raise and lower this topper, I want to see what kind of forces this mechanism is going to have to handle. And so there's going to be dynamic forces with the vehicle moving, and then there's going to be static forces with the vehicle standing still that this mechanism is going to have to absorb. So going down the road, you have aerodynamic forces either pushing the top down or possibly lifting the top. So if you look real hard and maybe squint a little bit, the top of the shell looks like the top of an airplane wing, which creates lift. So I don't know which one is happening to this truck. I don't have any kind of aerodynamic data, and I sure don't have access to a wind tunnel. So I will calculate what happens under the worst case condition, which is the lift. So it's going down the road and the wind is trying to pull the topper off the bed of the truck. Okay, so the mechanism again that you're designing to raise and lower the topper also has to handle these dynamic forces, because you don't want to be going down the freeway and all of a sudden your shell flies off the truck because the wind pulls it off the back of the truck. So you got to make sure you design it so it's going to be strong enough to be able to handle these aerodynamic forces. The other dynamic forces is going to be braking forces. I'm ignoring acceleration forces just because this truck is no speed demon and it can probably brake a lot harder than it can accelerate. So slam on the brakes. I don't want the shell slamming into the back of the cab of the truck. So again, whatever you're designing, it has to be strong enough to be able to handle all these different dynamic loads. Otherwise, the shell of this truck is going to just be moving all over the place, and it's going to constantly be wanting to fly off the truck. So you got to make sure whatever you're designing is going to be able to handle all these different types of dynamic loads. Same with going down a rocky trail. Okay, you're going to get the side-to-side motion where the movement of the truck is trying to throw the shell of the truck off to the side of the truck. Okay, so going down a trail is bobbing back and forth. You don't want the shell of the camper falling off on the side of the truck. Again, that would just ruin your day. So the mechanism that you're designing to raise and lower this truck has to be able to handle this side-to-side motion also. Has to prevent the top from falling off the truck. And then lastly, there's static loads. So you park the truck, the top is up, all of a sudden it starts snowing, and you have 5 feet of snow on top of your shell. Okay, so what does that do to the load? I mean, how much weight does snow add to the weight of the topper itself? So you have this downward force pushing down on the mechanism that you're using to raise and lower this topper, and that mechanism has to be able to handle the worst case condition plus some kind of factor of safety, because you don't want to be sitting in the back of the truck and all of a sudden the shell just collapses and comes down and smacks you in the head. It could cause serious personal injury. It can break your neck. It could hurt you. So whatever you design, you have to make sure it's going to be strong enough with a really decent factor of safety so that your shell doesn't fly off the truck when you're going down the road, and 2, it doesn't collapse under a heavy snow load, for example. So do your homework up front. Make sure you understand all these different types of loads that this mechanism that you're designing is going to have to handle, and that way when you're designing it, you can make it strong enough to handle all these different types of scenarios. To calculate the lift or downforce of an object, so for example, the first force, we didn't know if it was lift or downforce, so we're going to go with the worst case condition and think, all right, this topper is creating some lift in the back of the truck. So to calculate that, we need the surface area of the topper itself. The dimensions of the topper are 67 inches wide by 72 inches long, and that equals 4824 square inches. Now, I don't know how much pressure is being used to lift the top up or push the top down. I don't have access to a wind tunnel or any kind of aerodynamic data on these toppers, so I'm just going to do my best swag at it. And I just can't imagine this top having more than 2 psi negative lift. I mean, it just doesn't seem possible. even at 80 miles an hour, I don't think this top could produce more than 2 psi of negative lift. So let's go with that. So to calculate how much force is pulling up on the top, if we assume negative 2 psi lift, we would take the area of the topper, which is 4824 square inches, and multiply it by the pressure, which is 2 pounds per inch squared. And so now you have the inch squared go away, and all you're left with is the pounds. And so if you take that 4824 times 2, you get 9,648 pounds. All right, so highly unlikely that we're producing that much lift. Now, that doesn't mean we're not producing lift, but 9,000 pounds of lift, it would pull the back end of the truck up. The back end of the truck probably weighs 2,500 pounds. With 9,600 pounds, the back end would be up off the ground. So highly unlikely that there's even negative 2 psi lift. Even at 1 psi lift, you would get 4824 pounds. All right, so it'd just be the area times 1 psi. And even that is highly unreasonable. Again, the back end of the truck would be up in the air as you're going down the road. So I think as far as lift, as far as the topper creating lift, I think that's debunked. I think most likely there's downforce on the top, and that works in our favor. So it helps hold the top down to the truck bed, and so that definitely works in our favor. Now, as far as braking force, I think we said that the max G-forces that this truck could achieve when it's braking is 1G. Highly unlikely. I mean, a full-on Corvette will pull a little bit over 1G when it's braking, so this truck's not even close to 1G, but let's just assume it's 1G. So if the top weighs 200 or 300 pounds, basically at 1G, that top is sliding forward with a force of 300 pounds. So whatever mechanism that you're using to raise and lower this topper has to be able to handle that kind of force of the topper trying to slide forward. Otherwise, the topper's, every time you slam on the brakes, the top's going to want to slam into the back of the cab. Now the same goes with the truck going down a rocky road. So if this is a topper, you have that, we talked about this force going side to side trying to rock the top off the bed of the truck. So again, if we did 1G that way, 1G that way, so now this topper is putting a cycling alternating force of 300 pounds this way, 300 pounds this way. So again, whatever you design has to be able to take these kind of loads of just the top trying to slide back and forth off the back of the truck with a force of 300 pounds in each direction. All right, so now that we looked at some of the dynamic loads that the top might see, let's look at some of the static loads that the top might see. So say you're parked, you have the top up, and you have this horrible snowstorm come through, and so the snow is piling on top of your shell of the camper. So again, whatever mechanism that you design has to not only handle the weight of the shell itself, but also the weight of snow or whatever else you're putting on top of it. So if you want to calculate how much snow weighs, snow has a density of approximately 4 pounds per cubic foot. So if we take the area of the topper again, which is 67 inches, and I'm going to divide it by 12 to get it to feet, times 72 divided by 12, that would be equal to 33.5 square feet.
And if we assume that, let's take worst case condition. I don't even know if this is possible, but say you have 5 feet of snow piled up on top of the topper somehow. All right, so now we would take that 33.5 square feet times 5 feet of snow times the density of the snow, which is 4 pounds per cubic foot. So now again, the cubic feet, the feet go away, and so you're just left with pounds. And so now you're left with, let's see, 33.5 times 5 times 4. So you're left with approximately 670 pounds of snow on top of your roof. So if the topper weighs 300 pounds and you add the weight of the snow, which is 670, so now whatever mechanism you're designing has to at least be able to withstand 1,000 pounds of force pushing down on the top when it's in the up position. Because if, for example, you're sitting in that topper and you have all this weight above your head, you're sitting up straight, and all of a sudden the whole thing comes crashing down. So whatever you designed failed, and the topper comes crashing down and smacks into your head. You know, you don't want that to happen. You can break your neck, you can do serious damage to yourself. So whatever you're designing to hold this topper up has to be able to handle the worst case conditions. All right, so the first stress that we'll calculate is what happens when you slam on the brakes. So shown in the picture, slam on the brakes, the shell wants to move forward, and it wants to shear off that yellow tang that's attached to the square telescoping tube. So we want to calculate the shear strength of that tang because it's trying to fail and shear, not bending. So we need the area of the tang. So the area of the tang is 0.25 square inches. It's just the length times the width of the rectangular surface area of that tang. You can either calculate it or just get it off of SolidWorks. I just got it off of SolidWorks. The shear strength of the material, which is just mild steel, is 49,000 psi. So if you're trying to calculate what the shear strength of that, that this tang can handle, you take the area of that tang, which is 20.25 square inches, multiply it by the shear strength of the material, which is pounds per inch squared. So again, the inch squareds cancel out and you're left with pounds. And so with this equals 12,250 pounds. So each of these tangs, and you have 4 of them, can withstand 12,000 pounds in shear force. So even if this truck slams on the brakes and somehow pulls 1 G of force, if the top only weighs 300 pounds, that's what these tanks are going to feel. But again, each of these tanks can handle 12,000 pounds of force, so there's no problem with shearing the tang off with just braking force. Now, if you want to calculate the shear strength of the orange part, so the part that interacts with the yellow tang, we can do that too. So the area of that part is 0.141 square inches. Okay, so again, it's just the length times the width of that part. And again, the shear strength of the material is 49,000 psi. So 0.141 inches squared times the yield strength, or the shear strength of the material, and that equals times 49,000, so that equals 6909 pounds. Okay, so even the orange part can handle close to 7,000 pounds of force and shear. So both of the parts interacting, the orange part's actually going to be the weaker part, so, but even then it can still handle almost 7,000 pounds of force. Not even close. I mean, way far exceeding the requirements of being able to handle 300 pounds. And again, that 300 pounds, that's 300 pounds divided by 4, because all 4 mechanisms are handling that 300 pounds. So really even though this shear force rating is lower than that yellow Tang shear force rating, it's still way more than you need in braking force. So we're all good there. Now the other force that this top is going to see is the side-to-side rocking motion. You're going down a rocky road and the top is getting thrown side to side. So what kind of forces is the top going to see? Or what kind of forces are going to be imparted on the mechanism that holds the top in place? So again, it's that Tang, the tongue and groove mechanism, that we're going to be calculating. And believe it or not, the shear strength of that yellow part is going to be exactly as we calculated in the first part. So we took 0.25 square inches times 49,000 pounds per square inch, and that was 12,500 pounds. So the shear in both directions is theoretically the same. Now in real life, the side-to-side force is probably going to be less, because that Tang is going to want to bend. But as you can see from that picture, the mating part is so close to the bottom of that Tang that I'm not even going to bother calculating what the bending force was going to be, because it's just going to be very high. So as far as the side-to-side rocking motion, 12,500 pounds is what we can handle. Really the most it's going to see is 300 divided by 4. So we have a huge factor of safety here. Even the rocking side to side is not going to be a problem for this mechanism. All right, so as far as the static loads are concerned, mostly snow, but snow plus the weight of the topper. This is the mechanism that I'm going to use to lock the topper in place. So it's a push-pull pin, so it can lock in the open position, and when you twist it, it extends out. So this piece is going to be the piece in shear. This is what's going to be going through both of the walls of the telescoping parts, and this piece is 0.235 inches in diameter. Okay, so in order for this to fail, the load of that top has to be able to shear this pin off. Okay, so that's the only way this top is coming down, is if this pin gets sheared off. So let's calculate what the load is, what kind of load this can handle. So that diameter is 0.235 inches, and so the total surface area is pi r squared, which is 0.235 divided by 2 squared. And so 0.235 divided by 2 times 3.12 equals, so you have a total surface area of 0.37 square inches. Okay, so that's the area that we'd have to shear off on this pin. So I'm assuming that the linear actuator isn't contributing at all to the support of the top right now. I'm assuming that this pin is going to take the entire load. So this pin is actually a stronger material than the mild stainless that I'm using, but let's just go with the same shear strength of that material, so that we used before. So shear strength of the material that we used was 49,000 psi. The material in this pin is stronger than that, but we'll just go with 49,000 psi for the shear strength. So shear. All right, so now if we take the area of that pin, which is 0.37 square inches, times 49,000 pounds per inch squared for the shear strength, we get times 49,000, we get 17,963 pounds. Okay, so this pin, to shear that thick of a material, it would take 17,009, almost 18,000 pounds to shear that pin. And again, the total load that we have, the total snow load was approximately 1,000 pounds. So that 1,000 pounds was both the weight of the topper and the weight of 5 feet of snow on top of the topper. And again, this 1,000 pounds we can assume that it's being divided by 4 because we have 4 mechanisms holding that top up. So this pin may look dainty or a little bit on the small side, but it can handle a ton of shear strength. So we can handle more than this topper will ever see as far as snow loads or whatever else you're going to throw on top of that shell. The fiberglass is probably going to start to break before any of the mechanisms is going to start to break. So with this design, we have more than a good factor of safety in there. One of 4 of the uprights that I'm making. But this is what one of the uprights is going to look like. Normally I would send the files, my CAD files, out to get either water jet or laser cut, but since I'm on a budget, I just used a angle grinder with a cutoff saw and just cut it out a 3/16 inch plate. This is what my lifting mechanism looks like. So we have the linear actuator itself, and this linear actuator is attached to the telescoping rods, which are these 2 rods, which is pins. So it's just pinned top and it's pinned at the bottom. So the linear actuator doesn't have to handle any lateral loads. It only has to handle the loads of lifting and lowering the top. There's a bracket down here at the bottom that gets bolted to the bottom of the truck bed. And then this piece here, that's where the upright will bolt to on the telescoping rod. So let me show you it in action. All right, so now we have the telescoping rod extending. So you can see that the linear actuator has electronics built into it. So when it's fully extended, it shuts off automatically, and then when it's fully retracted, it shuts off automatically. One of the issues I need to fix is the slop that's in the telescoping tubes. If you can imagine, I have one at each corner of the truck bed. The top is fully up and it's windy, and you hear this all night. That could just make you crazy. So what I'm going to do is take feeler gauge and I'm going to tack weld it to the telescoping tube on all 4 sides to take away that slop. The upright will mount like this on the top. So it'll probably get 4 bolts, one on this lower level and then one on this upper level. I don't know where I'm going to put it here yet, but it's probably going to be somewhere towards the back of the truck. So once that's bolted on, the upright or the lifting mechanism gets bolted on at the top here and gets bolted onto the bed down there, and then there'll be 2 brackets, or there'll be a bracket right here that bolts into the side of the bed. And so I'll have this on all 4 corners of the bed.